So let us start on one of the most important ideas in analysis, which is continuity. Continuity of functions is something that is necessary to take derivatives to do any sort of analysis on functions. Well, that's slightly wrong. Any sort of nice analysis on functions generally assumes some sort of continuity. Of course, you can have some discontinuities. Not every function is going to be continuous. You're going to have jumps, but generally, the functions you consider when you're doing analysis are going to be somewhat continuous. Okay, so to say somewhat continuous or do any of these things, we need to know what continuous is, right? So first off, we defined what a limit of functions is. Definition: let x and y be metric spaces. Let x and y be metric spaces. And suppose e is a function. Suppose e subset of x and f maps e into y. Okay, and f maps e into y. Okay, and p is a limit point of e, and p is a limit point of e. We write f of x approaches q as x approaches p. We write f of x approaches q as x approaches p, or the limit x goes to p, f of x is equal to q, if for every so if there exists a point p in q in y, my bad, q in y, such that for every epsilon greater than 0 there exists a delta greater than 0, such that the distance in y of f of x comma q is smaller than epsilon whenever 0 is smaller than distance in x of x comma p is less than delta. Okay, note this does not mean that f of x is equal to q. This does not mean f of p is equal to q. Okay, and there are different distances also. Distances in x and distance in x and distance in y could be defined completely differently. Okay, also note that p need not be a point of e. P belongs to x, but p need not be in e. Okay, for every point x in e we have f of x defined, but p does not need to be even defined in e for this definition. Okay, and even if also right, even if p is in e, even if p belongs to e, p of sorry f of p need not be equal to need not be equal to limit x goes to p f of x. So in the first case, even if you are confused that, oh, the first one part f of p is equal to q might not happen because f of p is not defined. Even if f of p is defined, it might happen that they are not equal. Okay. So now, this is our definition in terms of epsilon delta. This also gives us a definition in terms of sequences that is going to be useful for us to prove certain results. Theorem 4.2. So while I'm writing this as a theorem, we will more or less use this as an alternate definition of limit, or I'm not, well, maybe not as an alternate definition of limit, but this will be one of the more useful ways we'll be using more useful results about limits that we'll be using. So let x, y, e, f, and p as in definition 1. So let x, y, e, f, p as in before. Okay. Then limit x goes to p, f of x is equal to q if and only if limit n goes to infinity, f of pn is equal to q for every sequence pn, for every sequence pn in E such that pn is not equal to p and limit of n goes to infinity, pn is equal to p. Once again, why is this condition here? Because you might say that, oh, I'm just going to look at the sequence p p p p p p p p p p p p p. Of course, that converges to p. But my definition of limit says delta greater than 0. So I am looking at points close to p, not including p. Okay, so that's why this condition is there. Proof. It's relatively simple. We want to show first this way. Choose pn in E such that pn converges to p. Okay, and then given epsilon greater than 0, there exists a delta. There exists delta greater than 0 such that, well, I am assuming the limit holds, right? Assuming that the limit f of x is equal to p. So there exists a delta such that dfy of f of x, comma q is smaller than epsilon if x belongs to E and what do you call 0 smaller than d of x, comma p is less than delta, right? Now, because pn converges to p, we know that there exists an n as Pn converges to P, there exists n such that n greater than n implies distance in x of Pn comma P is smaller than delta. Why is this greater than 0? Because I'm assuming Pn is not equal to P for every n. Okay? Well, therefore, for every n greater than n, dy of, since this distance is less than P, delta distance of f of Pn comma q is smaller than epsilon, right? Which implies, therefore, f of Pn converges to q. Okay? That's one way. Now let's look at the other way. We're going to do this by proving the contrapositive, which is to say, if limit f of x is not equal to q, then there is some sequence which does not converge to q. Okay, so suppose limit p goes x goes to p, x goes to p, f of x is not equal to q. Okay, what does that mean? It does not mean that, oh, it converges somewhere else. It might not even necessarily converge. Okay, but what that does mean is that then there exists some epsilon greater than 0 such that for every delta greater than 0, there exists some x delta belonging to E, which depends on delta, which is why I'm writing x delta. So, which depends on delta, such that for which distance of y f of x delta comma q is greater than or equal to epsilon, even though distance in x of x delta comma p is smaller than delta. Okay, let's do this. So how do I construct a sequence which does not converge to q? Well, take delta is equal to 1 over n, delta n is equal to 1 over n. For n is equal to 1, 2, 3, 4, example, n is equal to 1, 2, 3, and so on. And for each of them, find such an x delta n. And look at the sequence. Look at the sequence x delta n. Okay, then this does not converge to q. Then x delta n converges to p, but f of x delta n does not converge to q as required, and hence we have the result. Okay, so this is a very useful result because now we can just use the properties of sequences that we know to prove results about continuous functions. Okay, for example, corollary, one immediate result is that if f has a limit point at p, the limit point is unique. If f has a limit at p, this limit is unique. This limit is unique. Proof. We have shown before that the limit is unique for sequences. Limit is unique for sequences. Use 4.2. Use theorem 4.2. Okay, if there were two different what do you call it, limits, then a sequence Pn would have to converge to both the limit P1, Q1 as well as Q2. Well, that cannot happen because the limit of sequences is unique. Hence, this is unique. Okay. Here's a small definition. This is mostly self-evident, but I'm going to write it anyway. For complex functions, f comma g, both defined on E, both defined on E, f plus g of x is by definition f of x plus g of x. Okay. F minus g of x similarly is equal to f of x minus g of x. F times g of x is by definition f of x multiplied by g of x, and f divided by g of x, again by definition, is going to be f of x over g of x. However, this is provided g of x is not equal to 0. It is not defined whenever g is equal to 0. G of x is equal to 0. Okay? Similarly define for f comma g from E to Rk. Okay, in which case you might not have division, right? Because Rk is not a field, you cannot divide, you can add, subtract, you can multiply component wise, you might be able to divide component wise, but that's much more painful. Okay, you have to be careful about each component being non-zero. Okay, and however, you can define lambda f times x to be equal to lambda times f of x for lambda belonging to R. Okay? So what that allows us to do is now, instead of just being about R or something, we can still make some generalizations about limits for metric spaces. Theorem 4.4. Suppose, again, E is a subset of X, which is a metric space. I'm not going to write metric spaces and everything. Okay, I'll write this time a metric space. Metric space. P limit point of E. P limit point of E. F and G are for now complex functions on on E. F comma G complex functions on E, and that limit x goes to P f of x is equal to A, limit x goes to P g of x is equal to B, then A, limit x goes to P of f plus g of x is equal to A plus B. Surprise, surprise, who could have possibly guessed that? Limit x goes to P of f times g of x is equal to A times B. Okay? And C, limit x goes to P of f over g of x is equal to A over B, provided if B is not equal to 0. Okay? Proof. Again, from properties of sequences. Follow from properties of sequences. Okay? Note, if we replace complex functions by if we replace complex functions by f comma g from E to Rk, then A does not change. Okay, then A remains unchanged, but B becomes limit x goes to P f times g of x is equal to 8 times B, which is componentwise multiplication. Okay? So that is my definitions of limits of functions, and these are what I'm going to use to define what are called what are continuous functions. Continuous functions. Okay? And the definition of continuous should not come as a surprise to you. You have seen this before. We are just generalizing it to metric spaces rather than just reals. Okay? Definition. Suppose x and y are metric spaces. Suppose x and y are metric spaces. Metric spaces. Suppose E is a subset of X. Now P belongs to E, and F maps E to Y. and f maps e into y. Okay. Well, why are we taking p in e? It'll become obvious because we want continuous. So f of p should be defined. Then f is said to be continuous. Then f is said to be continuous. Said to be continuous at p if for every epsilon greater than 0 there exists a delta greater than 0 such that distance y of this time f of x comma f of p is smaller than epsilon whenever distance x of x comma p is smaller than delta and x belongs to e. Okay, which is to say, oh, the limit of the function at p should be equal to f of p. So f of p has to exist. Sorry, f of p has to exist and the limit must be equal to f of p. Okay. F is continuous if f is continuous at every point p at every point in E, then f is said to be continuous on E. Then, well, let me say this, off E. A very small point in E could be confused for in the interior of E. Okay, I don't want it to be interior, I want it to be including the boundary, so I'm going to say off E. And then f is said to be continuous on E, on the entire set E. Okay, so that is the definition of a function being continuous on the entire set. Okay. Note, if P is an isolated point of E, if P is an isolated point of E, then our definition implies every function which has E in its domain is continuous at P. Then every function f which has E as its domain. I mistakenly said in its domain before, but E, you not need to have E as its domain. If E is a subset, P might not be a isolated point of the domain, right? But if E is the domain, then it is an isolated point of the domain. Is continuous at P. Is continuous at P. Okay, that's because whatever epsilon you choose, you can always choose the delta such that x is the only point in that distance, right? And so, well, if x is the only point in that distance, f of x, f of p, well, p is the only point in that distance, not x. Then distance of f of p and f of p is 0, so it's always going to be less than epsilon. Term 4.6. Suppose we are as in the definition. also assume that P is a limit point of E. If P is a limit point of E, okay, so that we are not in the case that it's an isolated point, then F is continuous at P if and only if limit x goes to P, f of x is equal to f of P. Okay? Proof. Compare the two definitions. Compare the two definitions. Okay? Now, let us look at continuous functions. Let us look at some of the properties of continuous functions. Continuous functions are more or less nice. Okay? And the first nice thing we can say is, oh, continuous functions, if we add continuous functions, they are continuous because of theorem 4.4. Okay, if you subtract continuous functions, it's going to be continuous. If you multiply continuous functions, they're going to be continuous. What is not obvious is that the composition of two continuous functions is continuous. Let us prove that. Theorem 4.7. Okay. Suppose you have x, y, and z metric spaces such that E is a subset of X, F maps E into Y, which is F maps E into Y. G maps the range of F, which is F of E. G maps range of F, which is F of E, into Z. And let us say H is the composition of the two. Okay, H is the mapping of E into Z given by H of X is equal to G composed F of X, which is equal to G of F of X. Okay. Then, if F is continuous at P, if F is continuous at P belongs to E, and G is continuous at F of P, then H is continuous at P. Then H is continuous at P. Okay. Proof. You might have seen this proof before when you have shown things for a composition of functions. The idea is going to be the same. Let epsilon greater than 0. So given epsilon greater than 0, since G is continuous at F of P, as G is continuous at F of P, there exists a delta, which I'm going to call maybe delta G greater than 0, such that distance of z of f of p following nomenclature g of y comma g of y comma g of f of p is smaller than epsilon whenever, so if whenever, let me just say whenever distance in y of y comma f of p is smaller than delta g, and y belongs to f of e. Right? Now, since f is continuous at p, given delta g, given delta g greater than 0, there exists delta greater than 0 such that delta of y comma f of p, sorry, not y comma f of p, distance y of f of x comma f of p is smaller than delta g whenever distance in x of x comma p is smaller than delta and x belongs to e. Therefore, what that means is distance in x of x comma p is smaller than delta and x belongs to e implies distance in z of g of f of x and g of f of p 1, 2, 3 is smaller than epsilon. Okay? Therefore, that means h is continuous. H is continuous at p as required. Okay? So now the theorem that I'm going to write is more or less considered the definition of of continuous functions in non-metric spaces. Okay, this is a consequence in this case, but this is literally the definition in spaces which are not open spaces, not metric spaces. Theorem 4.8. Since I have not spent time defining what are open sets in non-metric spaces, we are not going to go into that. But for now, let's look at this result. I'm mapping f of a metric space x into a metric space y. F of a metric space x into a metric space y is continuous and continuous on x if and only if f inverse of v is open for every open v in y, is open in x for every open v in y. Proof? Okay, so as I said, this is more or less the definition. Okay, um, we're going to show if and only if. So first, let us assume this way. Suppose f is continuous and v is open in y. Suppose f is continuous on x and v open in y. Okay, what does that mean? Well, every point of v is an interior point of v. We want to show f inverse of v is open. We want to show f inverse of v is open, i.e. every point p in f inverse of v is an interior point of f inverse of v. Right? So suppose such a p exists. So let p belonging to x such that f of p belongs to v. Right? Now since v is open, there's an epsilon ball around f of p, which is contained in v. There exists epsilon greater than 0 such that f of p such that for every y belonging to y, distance in y of f of p, y comma f of p, just y comma f of p smaller than epsilon implies y in v. Right? Well, f is continuous. F continuous. Therefore, there exists a delta greater than 0 such that distance in x of x comma p less than delta implies distance in y of f of x comma f of p smaller than epsilon. Right? What does that mean? Therefore, x belongs to f inverse of v for every x belonging to x such that distance of x comma p is smaller than delta. Right? Therefore, the ball in x of radius delta surrounding r belongs to f inverse of v, and hence f inverse of v is open. Therefore, f inverse of v is open. Therefore, x interior, sorry, not p, x, p interior point of f inverse of v as required. So f inverse of v is open. Conversely, suppose f inverse of v is open for every v in v. Suppose f inverse of v is open in x for every open set V subset of Y. Okay, so, well, fix P belonging to X and epsilon greater than 0 such that um okay, sorry, and let V be the subset of Y is equal to Y in Y such that um distance of Y of, okay, so let V be the ball in Y centered at f of P of radius epsilon. Okay, well, this ball is open, then V is open, hence f inverse of V is open, hence f inverse of V is open, is open, right? And since it is open, therefore there exists a delta greater than 0 such that X belongs to f inverse V as soon as distance in X of P comma X is smaller than delta. Right, because it's open, there is some ball of radius delta at P, which is in f inverse of V. But what does that mean? Therefore, the X of P comma X smaller than delta is implying, well, that f of X belongs to V, implies f of X belongs to V, implies distance in Y of f of X comma f of P is smaller than epsilon. That's the definition of my V, and that completes the proof. Okay, so this is more or less the definition of open that is used if I don't have a metric space, but we haven't defined open sets without a metric space, so for now we are going to be fine. If you do ever take a course in topology, this would be the definition of continuous you're looking at. Okay, corollary. A mapping F of a metric space onto metric space is continuous of a metric space X into a metric space Y into a metric space Y is continuous if and only if F inverse C is closed in X for every closed C in Y. Proof? Proof? If C is closed, then its complement is open. C complement is open. And use the previous theorem. Okay? I'm going to write one more result and then stop for actually two more results and stop for now. Okay. Term 4.9. For now, we'll look at real and complex valued functions for just these two results. Okay. Rather than just random metric spaces, let f and g be continuous complex functions on a metric space X, on a metric space X. Okay, so Y is C, then F plus G, F times G, and F divided by G are continuous. On X. Okay. Proof. Well, at isolated points of X, there is nothing to prove. There is nothing to prove. Otherwise, use results 4.4. Otherwise, follows from term 4.4 and 4.6. Okay, that is for complex valued. We have a similar result for RK valued. A. Let F1 to Fk be real functions on a metric space Y. Be real functions on a metric space Y, metric space X, and let F be the mapping of X into RK, defined by f of X is equal to f1 of X fk of X belonging to X. Okay, then f is continuous if and only if, in fact, each of the functions f1 to fk is continuous. And secondly, well, this part is easy. If f and g are continuous, if f and g are continuous, then so are f plus g and f times g. Continuous mappings of X into R to the K, then so are F plus G, comma, F dot G. Okay. Note. F1 to Fk are called the components of F. F1 dot Fk are called components of F. Okay. Okay. Mm, Let me do this. Let me denote these by small bars over their head so that these are vector valued functions. Okay. So f1 to fk are scalar valued, f times g, f and g are vector valued. So now there are two ways of defining multiplication. F dot g, I said it's component wise, but I made a mistake there. F dot g is actually what do you call the dot product of the two functions, right? So you're doing the dot product as defined on RK, which is the sum. You do component wise multiplication, but then you add all of these. Okay, so f plus g is a vector valued map. Again, f plus g is vector valued, so is a mapping into RK. However, f times g is a real function. However, f dot g is a real function, is a real valued function. So I misspoke before also when I talked about f dot g. Okay, the f dot g is real valued where we are using dot product. Okay, proof. How do we prove? Part A follows from the inequalities. Part A follows from f I of x minus f I of y is smaller than or equal to f bar of x minus f bar of y, which is equal to, well, summation I is equal to 1 to k absolute value of fi of x minus fi of y squared to the 1/2. Right? Summation over all of these for I is equal to 1 to k. And part 2 just follows from part B, follows from theorem 4.9. Okay. Also part A, needing to show component wise. Okay. And so that proves this theorem. I'm going to stop here for today. This is what continuous functions is. We have looked at some of these things. We'll continue on this tomorrow.